The first law of motion, the law of inertia. Objects will remain at rest or in a uniform motion in a straight line unless acted upon by an unbalanced force. Here we have 3 spheres on a table in a state of rest. The gravity pulling the spheres down is countered by the force of the tabletop pushing the spheres up in the exact opposite direction. The balance of forces is what keeps the spheres at rest on the table. This sphere will act as an unbalanced external force. Without another force to counter its movement in the opposite direction, it becomes an unbalanced force acting on the other spheres. The external force collides with the spheres and changes their motion state. The natural tendency of an object to remain at rest or in a uniform motion in a straight line is called inertia. The second law of motion, the law of force, mass, and acceleration. The acceleration of an object depends upon its mass and the magnitude of the force applied to it. When an unbalanced force acts upon an object, the motion of the object changes. The rate of this change over time is called acceleration. Acceleration depends upon 2 variables: the mass of the object and the magnitude of the applied force. In this example, a 3D character represents a pulling force on a 50 kilogram mass. Using his full strength, he has no trouble accelerating the object in the direction of his pulling force. If the mass is doubled and we want to accelerate it at the same rate, we must also double the force. Our character, however, is already pulling at his full strength. So what happens? He can only accelerate the object at half the rate as illustrated by his slower pace. This relationship between force, mass, and acceleration is the source of one of the most important equations in physics. Force equals mass times acceleration.
Oh, hello. Welcome to my laboratory. My name is Professor Mack, and today I'm going to be talking about Newton's second law of motion. This is one of 3 laws which Sir Isaac Newton published in 1687. The laws explain the interaction of forces and objects, and the way in which the motion of an object is affected by force. The second law is an incredibly important law, even although its form is rather simple. You may have seen it before, and it's normally expressed as F equals ma. Today I'll explain this law, and together we'll explore the way in which we can use it to predict how an object will change its motion when an unbalanced force acts upon it. So what does the F, the M, and the A stand for? Well, F represents the force on the object, M represents the mass of the object, and A represents the acceleration of the object resulting from the applied force. So using this equation, it is possible for us to calculate the force acting on an object of known mass by observing the object's acceleration. Alternatively, by rearranging the equation, we're able to predict the acceleration of an object of known mass as a result of the force acting on it. So you can see that this equation is very useful. Now you should note that F equals ma is in fact derived from the more exact definition of the second law, which is that the force equals the rate of change of momentum of the object, where momentum is defined as the object's mass times its velocity. However, today we'll study the law in the form F equals ma, and the best way for us to do that is to do an experiment. Okay, well, here is our experimental setup. We have a block of wood here representing our object, and as you can see, it is resting on a very smooth surface, which is so smooth we can assume that it provides no resistance to the block moving on it. We also have a loading device here, which we'll use to apply a constant force to the block as it moves along the surface. We'll be able to measure the force being applied to the block by observing this Newton's spring balance. This uses a spring which has been calibrated to read force in newtons. As the loading arm moves, it exerts a force on my hand through the extension of the spring, and we get a reading of the force being applied as shown by the scale here. So let's do an experiment to better understand Newton's second law of motion. Remember that it states that force equals mass times acceleration. Now, a very important point to note is that the force refers to the sum of the forces on the object in a given direction. For example, let's look at the forces in the vertical direction on this block. We have the gravity force and the force from the table onto the block. These are in balance, and therefore the net force on the block in the vertical direction is 0. So what does F equals ma tell us about the vertical acceleration of the block when the sum of the forces in the vertical direction is 0? Well, let's write down the equation and see. We start with the sum of the forces in the vertical direction equals the mass of the block times the vertical acceleration. That is F equals ma, with the subscript v used to indicate that we are considering the forces and acceleration in the vertical direction. We then rearrange the equation to give the sum of the forces in the vertical direction divided by the mass of the block equals the vertical acceleration. So taking the sum of the vertical forces equal to 0 newtons, with n being used to represent newtons, taking the mass of the block as 5 kilograms, and then using the equation for acceleration, we see that this gives 0 newtons divided by the mass of 5 kilograms, which equals the vertical acceleration. And since 0 divided by 5 equals 0, it follows that the vertical acceleration is 0 with the units meters per second squared. We can see that this is indeed the case by observing that the block is not moving. So what if we introduce an unbalanced horizontal force? Well, the second law tells us that if we have an unbalanced force, we will observe the object accelerating. So let's do that and see what happens. Well, we're ready to perform the experiment. As the block moves along the surface, we will take a snapshot of the position of the block at 1 second intervals. This will help us identify the change in motion of the block. The block has a mass of 5 kilograms, and we will apply a force of 2.5 newtons. So let's see what happens. Well, we have the snapshots of the positions of the block at 1 second intervals. You can see that the distance between the snapshots increases. This means that the velocity of the block is increasing, which means that the block is accelerating under the action of the force. We can check the force which was applied by looking at the recording of the Newton balance during the test. It was attached to the block through a magnetic link between the end of the Newton balance and a magnetic insert in the block. Once the test starts, you can see that a force of 2.5 newtons was applied. Remember that the surface here provides no resistance to the motion, so the measured force is the only horizontal force applied to the block and is therefore the unbalanced horizontal force. So what will happen if we apply a force twice as large? Let's apply a force of 5 newtons to the block and see what happens. Well, looking at the snapshots at 1 second intervals, you can see how the block has moved a further distance for each second under the action of the larger 5 newtons force. This is a result of the larger force increasing the acceleration of the block. If we have a look at the recording of the Newton balance during the test, we see that a force of 5 newtons was indeed applied to the block. So now that we understand the way in which the second law works, let's use it to predict the force required to accelerate a block 10 times the mass of the smaller blocks. Our challenge is to predict the force we need to apply to this large block of 50 kilograms to achieve the same acceleration experienced by the small 5 kilograms block when it had a force of 5 newtons applied. So let's use Newton's second law to calculate the force required. We first have to calculate the acceleration of the small 5 kilogram block with an unbalanced force of 5 newtons applied. The subscript S indicates that we are referring to the small block for this part of the calculation. We calculate the acceleration by writing the second law in the form force divided by mass equals acceleration. So taking the unbalanced force equal to 5 newtons and the mass equal to 5 kilograms, this gives 5 divided by 5, which equals 1 meter per second squared. To calculate the force required to accelerate the large block at 1 meter per second squared, we use the second law in the form force equals mass times acceleration, where the subscript L indicates that we are referring to the large block for this part of the calculation. So taking the mass of the large block as 50 kilograms and the acceleration the same as the acceleration of the small block, which we calculated as 1 meter per second squared, this gives the force we need to apply to the large block equal to 50 kilograms times 1 meter per second squared, which gives 50 newtons. Now this is interesting, since you can see Newton's second law has told us that for a block with a mass 10 times larger, we need to apply a force 10 times larger to get the same acceleration. In other words, to achieve a given level of acceleration, more force is required to accelerate an object which has more mass. So let's apply a force of 50 newtons to the large block and see what happens. I've lined up the centre of the large block with the centre of the small block at time 0, so that we may observe the relative motion of the blocks by observing the positions of their centre points. So let's run the experiment. While comparing the positions of the snapshots for the large block with a force of 50 newtons applied and the small block with a force of 5 newtons applied, we can see that the distance between the snapshots at 1 second intervals are the same. This is because they are accelerating at the same rate, just as we predicted. And if we have a look at the recording of the Newton balance during the test, we see that a force of 50 newtons was indeed applied to the 50 kilogram block. So there we are. That's how you use Newton's second law to control the motion of an object. So let's review what we've learned about Newton's second law of motion. The law is expressed as force equals mass times acceleration. We noted that the force is the sum of the forces on an object in a given direction. If this equals 0, then the acceleration of the object is 0. We also observed that if we have a non-zero unbalanced force applied to the object, it will accelerate. The larger the force, the greater the acceleration. And for objects with larger mass, we need to apply a larger force to get the same acceleration as a smaller block with a smaller force applied. Well, thank you.
The third law of motion, the law of action and reaction. For every action, there is an equal and opposite reaction. A direct example of the third law is the rocket engine. Look at the hot gases streaming out of the shuttle's engines. If this is the action, what is the equal and opposite reaction? It becomes clear as the shuttle is propelled into the sky. The reaction to the gases escaping from the engine is the pushing of the spacecraft in the opposite direction. Everywhere you look, these laws are being followed by everything around you. With some extra awareness, you may begin to recognize your own use of these laws in your daily life.
Ionic bonding occurs between two atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has one valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion.